In this video, we're going to look at what happens when we have a weak base, when we have a weak acid and a strong base being titrated together. And so the setup in this case is going to be that we have HA and sitting in a beaker with a pH probe. So our weak acid's in the beaker, that's our analyte, and our titrant is going to be OH minus. So that's our strong base. And we're going to look at the titration curve. And a couple of things right off the bat. So if you look at this titration curve, you're going to notice a few different things. So for this one, our initial point, you'll notice, is going to be much higher than our initial point for the strong acid titration curve. So our strong acid titration curve started somewhere down here at around 0. Our weak acid, on the other hand, even though we're going to find out that this starts at the same exact concentration as the strong acid, so this is going to be 1 molar, for example. Even though it's 1 molar, our pH is much, much higher than 0. And that's because the weak acid only partially ionizes. So we know that it's in equilibrium. And so this is why we get a lower pH than if we were to have a strong acid. So this very, very first point where we've added, and down here, this is the volume of the titrant that's been added. And so we're at 0. And so this very first point is if we were to just go and measure the pH of a weak acid solution. So we'll call this point A. And so what we have is we just have a weak acid in solution. No base has been added just yet. So this is a very easy problem to solve. This would be the same thing as saying that you have 1 molar acetic acid, calculate the pH if the Ka is equal to 1.7 times 10 to the minus 5. So this is a classic type 2 problem. So if you go back and look at the type 2 problems, and this is basically just going to be an ice table. Right? So we have the Ka, we have the concentration of the acid initial, and it wants us to get the pH from that. So if you had to calculate the pH at the very, very beginning of this, where you just had the acid with no base added yet, that's what you're going to use. You're going to use the Ka and the concentration to get the pH. And we'll see that in just a minute. So we haven't even started the titration yet. And so now our equivalence point, let's go to where our equivalence point is going to be. So our equivalence point is going to be at the inflection point. And something interesting happens here. So our inflection point is not at pH 7, but our inflection point is somewhere greater than pH 7. So this is going to be point B. And so the question is why is the pH greater than 7? So let's say, for example, that we started this with 1 mole of HA, like we did in the previous example, where we sort of did this conceptually. So if we start with 1 mole of HA, and we get to the equivalence point, that means that I'm going to need 1 mole of OH minus. And so in this case, we're going to subtract our 1 mole away, we're going to subtract our 1 mole away, and we're going to have 0 moles of OH minus, and we're going to have 0 moles of HA. So we have no acid, and we have no strong base. And we're going to start with 0 moles of A minus, and we're going to add our 1 mole to that. So we're going to have 1 mole of A minus around. So at the equivalence point, we have 100% A minus present. Now, unlike in the case where we had a strong acid and strong base, A minus is the conjugate base. And so therefore, it is a base in this case. So A minus will react with water to make OH minus and HA. So we saw this problem, this type 2 problem, in the hydrolysis section. So if you go back to the video that talks about hydrolysis of salts, you'll see that if you have the conjugate base as an anion in the salt, it will react with water to make OH minus and HA. So at the equivalence point here, we're going to have some OH minus around because of the A minus. And so this is also a type 2 problem, which is an ice table problem. And basically what we're going to do is we're going to get the Kb, and we're going to convert the Ka to a Kb using Kw. So we're going to have the Kb. We're going to have the concentration of the base initial, and we're going to get a pOH out of this, which we can convert to a pH using a standard ice table setup. So that's sort of puts us on the map between the two major points. Now let's look at what happens between A and B. So at A and B, we know from our last example that our excess reagent is going to equal our HA. Our limiting reagent is going to equal our OH minus, and the pH, in this case, is going to be controlled by Henderson Hasselbach. So let's talk about Henderson Hasselbach a little bit and why that applies here. So let's go back and set up our stoichiometry table to be in this range. So if we have 1 mole of HA, and let's say, for example, we have, let's say we add 0.2 moles of OH minus, and of course we start with 0 moles of A minus in this reaction. So we have 1 mole of HA, we add less than an equivalent of the OH minus, so 0.2 moles. Let's figure out where we are in terms of our HA, OH minus, and A minus. So if we subtract our limiting reagent, which is the 0.2 moles, that's going to give us 0 moles of OH minus. So we subtract our 0.2 moles from the HA, that's going to give us 0.8 moles. And we add our 0.2 moles to A minus, and we get 0.2 moles. This is going to look like our setup from before. This is making a buffer. This is the making a buffer question. We have HA and A minus present in solution, and so we can use Henderson Hasselbach to get us our pH by using the pKa and the relative amounts of A minus and HA from that fundamental pKa, which is going to set the pH, and we can get it. So in here, we call this region the so-called buffer region from A to B. And that's basically making a buffer. What we're doing is we're taking a weak acid, we're converting some of it by adding a strong base to A minus. We have a mixture of HA and A minus in this region. And so that's why it's a buffer. And so that is what we're going to do with that is we're going to Henderson Hasselbach it. Okay, and so now the next question is well, let's go up here and we'll call this point C, which is where we've added a lot of base. So what goes on from B to C? So in this case, our excess is now going to be OH minus. Our excess is now going to be OH minus. Our limiting reagent is going to be HA. And so how are we going to work this out? So let's go to our table and figure this out, what we're going to do with this one. So in this case, let's say that we have 1 mole, and we're going to add to that 1.5 moles. So we have an excess of OH minus, and we start with our 0 moles of A minus. So in this case, our limiting reagent is now going to become our HA. So we're going to have minus 1 mole. This is going to give us 0 moles. We're going to do minus 1 mole from this. This is going to give us 0.5 moles. And we're going to do our, we're going to add to this our plus 1 moles to our A minus. So we're going to get 1 mole here. So what we have in solution is we have a mixture of OH minus and A minus. Now, in theory, what you could do here is you could set this up as a full-blown kind of common ion problem. If you go back and you look at the case where we have a strong acid and a weak acid present together, we found out that because the strong acid is strong, that it controls the pH. Well, and this is going to be true here as well. We have excess strong base, and that is going to control the pH, or really the pOH. And so the concentration of OH minus is going to equal the moles of OH minus in excess divided by the total volume, and then we can get from that the pOH and the pH. So there's one more point that we have to talk about on this titration curve that's really important, and it's something that we call the 1/2 equivalence point, so D. D is what we call the 1/2 equivalence point. And so why would the 1/2 equivalence point be important? And it has to do with the Henderson Hasselbach. So we're in the buffer region here, and so our pH is being controlled by the fact that it's a buffer. So let's look at that particular spot and see what's going on with that and why that's important. Okay, so at the 1/2 equivalence point, that would be where I've added 1/2 of my number of moles of HA. So this would be 0.5 moles of the OH minus. So that's what I mean by 1/2 the equivalence point. We're 1/2 way to the equivalence point, which is where the moles of HA is equal to the moles of OH minus. So let's see what the significance of that is in terms of this graph. So if we look, when we do our limiting reagent table and we subtract our 0.5 moles, we get 0 moles of the OH minus. And we're going to subtract away, and so we're going to get half of our HA, which is 0.5 moles. And then on the other side, we're going to add 0.5 moles of the A minus. And what you're going to notice is that at the 1/2 equivalence point, the concentration of the HA is equal to the concentration of the A minus. And so the same thing, the number of moles of HA is equal to the moles of the A minus. And so at this point, pH is going to equal pKa, because when we have the concentration of HA is equal to A minus, the log of A minus over HA goes to 0. And so we can get two things out of this strong acid and strong base titration, this weak acid and strong base titration. So one, at the equivalence point, we can calculate the concentration of the weak acid. So at the equivalence point, we can get the concentration of the weak acid by taking the number of moles of the strong base, dividing it by the initial volume of the weak acid, and get the concentration. And so 2, at the 1/2 equivalence point, we can get the pKa of the acid and the Ka by, if we could figure out what the Ka is from the pKa. So those are the two main things that we can get from this graph, is the concentration and the pKa, and that comes from the equivalence point and the 1/2 equivalence point. Okay, so here we go. So we have 50 mils of a 0.1 molar HCHO2 solution is titrated with 0.2 molar NaOH. So this is a classic weak acid strong base setup. Now it says the pH at 1/2 of the volume required to reach the equivalence point is 4.00. Calculate the Ka. So here's why I mentioned that point D is really important. So this is information at the 1/2 equivalence point. And so the pH at this point is equal to 4.00. So we know that because this is the 1/2 equivalence point, this is equal to the pKa. So if we take 10 to the negative 4, this is going to give us a Ka equal to 1.00 times 10 to the negative 4. And that's important because we're going to need that Ka for the following sequence of questions. So now it says calculate the pH of the acid after adding the following volumes of NaOH. So we have 0 molar, 15 mils, and 25 mils. So what we're going to do is we're going to work each one of these out down below. And I'm going to highlight which one we're working on by underlining it as we go along. Okay, so we're going to start with the 0 mils. So now if you remember, at 0 mils, so we're going to kind of sketch out our titration curve here. We haven't added any base yet, so we know that all we have in solution is HA. So what we're sitting with here at 0 mils is a solution that is 50.0 mils of a 0.10 molar HCHO2 solution. And so what's happening in this solution is we have HCHO2, that's reacting with water to give us CHO2 minus plus H3O plus, because it's a weak acid. And so we can set up our ice table and get this problem solved using our ice table and Ka. So our Ka expression in this case is going to equal the concentration of CHO2 minus times our concentration of H3O plus divided by our concentration of HCHO2, which is our weak acid. And so if we do our ice table, you're going to start to see me kind of do things quicker now. What we're going to get from our ice table, so you have to go back and watch the video. We're going to start with 0.10 molar, 0 molar, and 0 molar. I'm not even going to write out the full ice table because you guys should know at this point what I'm basically doing. So we're going to get minus X, and plus X, and so we're going to get X, and 0.10 molar minus X. So if we plug that into Ka, we're going to do our approximation here. So we have 1.00 times 10 to the minus 4, We're going to check our approximation, so we get H squared over 0.1 molar minus X. We check to see if 0.1 molar divided by 1.00 times 10 to the minus 4 is greater than 100. It is. So we can eliminate our X. And so we solve this by taking 1 times 10 to the minus 4th times 0.1, and then we take the square root. And so X in this case is going to equal 0.00316 molar, which is our concentration of H3O plus. And so our pH is going to equal 2.50. So if any of this seems unfamiliar, you should watch the video that discusses a type 2 problem of a weak acid at the very beginning. It was one of the first videos that talks about the type 2 problems. Okay, so in the second part of this, we're now going to look at the 15 milliliter case. So what we have to do now is we have to recognize that what we're doing is we're taking this HA and we're adding some OH minus. So in the first condition, we hadn't added any OH minus. We just had the HA hanging around. Now we've added some OH minus, so we're going to have our case where we make some A minus from this and our OH minus. So we're going to have to do a stoichiometric table with this. And the first thing we're going to have to do is we're going to have to get our number of moles. So for our moles of HA is going to be 0.050 liters times 0.10 molar, which is going to give us 0.005 moles of the HA. And so we can, for the NaOH, we have 0.015 liters times our 0.2 molar, which is going to give us 0.003 moles of the OH minus. So when we set up our stoichiometric table, we're going to have 0.005 moles of HA, 0.003 moles of OH minus, and 0 moles of A minus. So we recognize that our limiting reagent is the OH minus. And so that automatically tells us a couple of things. We know that number 1 from the stoichiometric table, we're going to be in the buffer region. And so we know that we're going to have Henderson Hasselbach controlling us at this point. So those are the two things I get from that stoichiometric table right away. So I have no more strong base left over. And I'm going to have a mix of my HA, which is going to be 0.002 moles. And I'm going to add my 0.003 moles to the A minus. So another thing that I can get right from here is I can see that my A minus is greater than my HA. So I'm expecting my pH to be greater than pKa from my Henderson Hasselbach. So that's just something that I check at this point. It's a good thing to sort of get your head straight at this stage. You look to see how much HA and A minus you have, and you can kind of get a feel. If you have a little bit more A minus than HA, pH is going to be greater than pKa. If you have less, pH is going to be less than pKa. If they're equal, then pH is going to equal pKa. So we plug this into Henderson Hasselbach. pH is equal to 4.00. And I get this by taking my Ka and converting it to a pKa, plus the log of the A minus over HA. And in this case, the A minus over HA is going to be 0.003 moles divided by 0.002 moles. And so my pH from this is going to be 4.176, and so I get 4.18. And that makes sense because A minus is greater than HA, so we get something a little bit higher than the pKa of 4. So in this case, what we're going to do is we're going to set up our stoichiometric table one more time. And so we still have 0.005 moles of the HA. I figured that out in the last one. If you figure out the number of moles of OH minus, this is going to be 0.005 moles of the OH minus. And so now we've reached a full-blown equivalence point. These two numbers are the same. So let's take a look and see how this problem works out. So if I subtract my 0.005 moles from both of these, I get 0 moles of HA and I get 0 moles of OH minus. And I add my 0.005 moles of the to the A minus, so I get 0.005 moles of A minus. So I recognize that this problem is 100% pure A. So all I have in this case is a weak base. And so what I'm going to do is I'm going to get my concentration of that weak base. So the concentration of A minus in this case is going to equal 0.005 moles divided by my total volume. So my total volume is going to be 50 mils plus 25 mils is equal to 75 mils. So I divide this by 0.075 liters. And so this gives me 0.0667 molar. We figured out that our concentration of A minus was 0.0667 molar. This A minus in water is going to react with water to make OH minus and some HA. So I can write that Kb in this case, because it's a base, is going to be my concentration of OH minus times my concentration of HA divided by my concentration of A minus. And so in this case, we need to get a Kb. And to get a Kb, what we have to do is we have to convert our Ka to a Kb. So we say that Kw is equal to Ka times Kb. And so if we solve for a Kb by taking 1.0 times 10 to the minus 14th divided by 1 times 10 to the minus 4, we get our Kb as 1 times 10 to the minus 10. So we have our Kb as 1 times 10 to the minus 10. And now it just becomes an ice table. So our concentration is 0.0667 molar. We start with 0 molar and 0 molar for the OH minus and the HA. We do minus X, and plus X. So we get 0.0667 molar minus X, and X. And so now we can plug this in. So we get 1.0 times 10 to the minus 10 is equal to X squared over 0.0667 molar minus X. We check our approximation is 0.0667 divided by 1 times 10 to the minus 10 greater than 100, and it is. So that means we can get rid of our X. And so if we solve for X by multiplying the Kb times the 0.0667 and taking the square root, what you get is you get that X, which is equal to the concentration of OH minus, is equal to 2.58 times 10 to the minus 6th. And so we can get a POH from that equal to 5.59. And so our pH is equal to 8.41. So this proves that for a weak acid, the equivalence point is going to have a pH greater than 7. So we actually just proved that arithmetically here, and the pH in this particular instance would be 8.41. Okay, so the last condition we're going to look at is where we have 30 mils. So if we go back to our mole table, our stoichiometric table, at 30 mils, this is going to be 0.005 moles of the HA. This is going to give us 0.006 moles of the OH minus, and we're going to start with 0 moles of the A minus. So our limiting reagent now is going to be our HA. So we know that we've gone past the equivalence point. So from this, I know that we are in region B to C, and so the pH is going to depend on the fact that we have strong base present in the solution. So let's prove that. So we subtract our limiting reagent from the OH minus. So this is going to give us 0 moles of HA, 0.001 moles of OH minus, and we're going to get plus 0.005 moles of the A minus. Now in this case, the OH minus is strong, and so that is going to control the concentration of OH minus in the solution. It's much, much stronger than the A minus, and so we're going to basically ignore the A minus because we're going to basically say that the A minus approximates out to having no effect on the OH minus concentration. And so we're just going to be dealing with the concentration of OH minus from the strong base. So we're going to get a concentration of OH minus by taking our 0.001 moles. We need a total volume. And so I have my 50 mils that I started with, that's from above, plus my 30 mils of base that I added. So this gives us 0.080 liters. And so our concentration is going to be, this is going to equal 0.0125 molar. And so if I want to get a pOH from this, I can take the negative log of that, and I get 1.90 for my pOH, and so this gives me a pH equal to 12.1. And so now I'm well above the equivalence point, and my pH is being controlled by that strong base that's in excess. So that is the main points along the titration curve, where we start with no base added to a point in the buffer region, to the equivalence point, to a point past the equivalence point. And all of these, so the thing that I want to stress is that all of these calculations are all done in previous videos. There's nothing new here. It's just a matter of using what we already know to calculate things as it relates to a titration curve.